that has definite helicity, and that's what's called a Weyl fermion. Helicity is only a Lorentz invariant notion for a massless fermion. A massive fermion could be at rest, and then there wouldn't be a distinguished axis around which to try to rotate to measure the helicity. So only a massless fermion has well-defined helicity. And in our derivation, we started with the massless Dirac equation. The massive Dirac Hamiltonian, which actually we'll consider later, would have an extra term that doesn't commute with gamma 5. So technically, we can't make this two-component reduction because the mass term would not commute with gamma 5. But perhaps more physically, the massive fermion doesn't have a well-defined helicity because it could be studied in its rest frame. Anyway, in relativistic physics, there's a notion of a massless Weyl fermion whose Hamiltonian is sigma dot p times plus or minus the speed of light. Now, there's also a corresponding antiparticle, which in condensed matter corresponds to the hole rather than the electron. It has opposite helicity somewhat as it has opposite charge. So, for example, nowadays we know neutrinos have masses, but in the old theory of the massless neutrino, the neutrino was a Weyl particle that had a definite negative helicity, and the corresponding antineutrino would have a definite positive helicity. So, to a very good approximation, the neutrino is a Weyl particle, although we nowadays know that that's not quite the whole story. So, the chiral Dirac Hamiltonian, which remember was sigma dot p, so the sigma matrices are 2 by 2 matrices, so in condensed matter terminology you would say it defines two bands corresponding to the two eigenvalues of sigma dot p. And so I've schematically drawn it here. The energy momentum spectrum is a cone. Well, the picture doesn't properly convey the fact that momentum space is three-dimensional. The picture makes momentum space look two-dimensional. So the picture looks more like the energy momentum relation for a massless Dirac fermion in 2 dimensions. But you're supposed to imagine that the horizontal directions are three-dimensional, and then the cone would be describing the two bands for a massless Weyl fermion in 3 dimensions. Now, for the generic 2 by 2 grand crossing, we found the Hamiltonian that was generically a sigma matrix times p times some generic matrix ajk. Except I dropped here the constant p star. So previously I wrote that as p minus p star, where p star was the position of the band crossing. I guess here I've written it as if p star is 0. Or we're measuring p relative to the position of the band crossing. So this is the same Hamiltonian as the relativistic Weyl fermion, except c times p has been replaced by some matrix times p. So what that means is that the fermion modes near p equals p star, well, obviously in condensed matter physics they won't travel at the speed of light. They'll travel at a velocity that's more like alpha times 1 over 137 times the speed of light. But they also won't necessarily propagate isotropically. If there are no particular symmetries, then the matrix AKJ is a random matrix, more or less. And you see, the natural metric governing these modes is not, well, for the relativistic Hamiltonian, the energy was the square root of p squared, where p squared is defined using the standard Euclidean space distance function. But for this mode, we have to define p squared using in such a way that not the Euclidean components of p, but the Euclidean components of a times p are orthonormal. So the natural metric that governs these modes is like so. Or in other words, the effective metric seen by this Weyl fermion is this one. So generically it will propagate, of course, much slower than the speed of light, but also anisotropically in our crystal. It will propagate anisotropically because since we assume no particular crystal symmetry, it has no reason to propagate isotropically. Now finally, and very importantly, the chirality of the gapless electron mode is given by the sign of the determinant of this matrix. Now, so in the relativistic case, the matrix was 1 or minus 1. So its determinant was 1 or minus 1. So in the condensed matter case, we have a completely generic matrix A, and our only condition on it is that it's invertible. Otherwise, we would not get this Dirac-like spectrum near P equals P star. If A had a zero mode, then we would have to make the expansion of the Hamiltonian to higher orders in the power series near P equals P star. So we're assuming that A is invertible, and there are two classes of invertible matrices that are continuously connected. There are those of positive determinant and those of negative determinant. The ones of positive or negative determinant can be continuously connected to the matrix 1 or minus 1 that we would have had relativistically without passing through a zero mode. So the sign of the determinant is the analog of the sign 1 or minus 1 in the relativistic Hamiltonian and tells us whether our gapless electron mode near P equals P star is chiral or anti-chiral in relativistic terminology. So a gap crossing in which the determinant is positive or negative is the analog of a relativistic massless chiral fermion, also called, as I've told you, a Weyl fermion, with gamma 5 equals 1 or minus 1. Now, however, we should remember something about relativistic quantum field theory in 3 plus 1 dimensions. And the fact I'm about to mention is quite important in the standard model of particle physics. A theory of the U1 gauge field of electromagnetism coupled to a massless chiral charged fermion of 1 chirality with no counterpart of the opposite chirality is anomalous. That's the analog in 3 plus 1. It's inconsistent. It can't be quantized in a gauge-invariant fashion. That's the analog in 3 plus 1 dimensions of the fact I told you in 1 plus 1 dimensions that the theory of right-moving electrons with no left-moving electrons would be inconsistent. And we saw in terms of band theory why band theory didn't give us an inconsistent theory. It came because of the fact that whenever there was a positive band crossing through the Fermi level, there was a corresponding negative band crossing. So when we start finding band crossings in one dimension, band crossing simply meant that the bands passed through the Fermi level. But in 3 plus 1 dimensions, I'm using the term band crossing to mean that two bands actually meet. And when we start having bands meeting in 3 plus 1 dimensions, we're in danger of getting a low energy effective description that, according to relativistic physicists, is inconsistent. So we should find a reason that that doesn't happen in a well-defined condensed matter system. So in 1 plus 1 dimensions, we avoided it because of this simple topological fact that we discussed, that epsilon of P passes through the Fermi level upwards as many times as it passes downwards. And we need an analogous topological theorem that will save the day in 3 plus 1 dimensions. This is the Nielsen-Ninomiya theorem, which originally was motivated to explain difficulties that had been found in constructing certain lattice gauge theories for fermions. So people were constructing lattice gauge theories for fermions to simulate the standard model on a computer, and some of the things you wanted were hard to construct, and Nielsen and Ninomiya theorem invented their theorem. Sorry. Nielsen and Ninomiya formulated their theorem to explain some things that had been observed in lattice gauge theory, but the same things go into explaining why a well-defined condensed matter system won't give the forbidden situation with a positive chirality Weyl electron and no negative chirality one. So I want to explain how this comes about, and you'll see that it will involve a reprise of things that you've heard about in Charlie Kane's lectures. So in formulating the theorem, we're going to assume that the band Hamiltonian H of P is gapped except at finitely many isolated points in the Brillouin zone. So the Brillouin zone is really a torus, a three-torus in 3 dimensions, but it's sometimes convenient to think of it as a polyhedron with boundaries that are defined by certain conditions. And anyway, that makes it easier to draw because it's hard to draw a torus. So I've kind of drawn a polyhedron, but we're supposed to identify opposite sides and make it a torus. And then there are finitely many bad points that are drawn in red. And these bad points are points where band crossings occur. And a band crossing could have positive or negative determinant for the matrix of derivatives of the Hamiltonian, the matrix that I call little a. And the Nielsen-Ninomiya theorem says that there will be as many positive chirality band crossings as negative chirality ones. So we want to explain how that comes about. We'll attach an integer to each of the bad points and show that the integers add up to 0. To get started, we'll assume there are only 2 bands. Also, by simply subtracting the C number function from h of p, we can make h of p traceless without changing the band crossings. So we can assume that h of p is b of p dotted into the sigma matrices for some vector valued function b of p. Now, away from the bad points, b of p is not 0 by definition. The band crossing happens exactly when b of p is 0 and the 2 bands are degenerate. Whenever b is not 0, b dot sigma has unequal eigenvalues. So the bad points are exactly when b of p is 0. And where b of p is not 0, we can define a unit vector, n of p, which is b divided by its magnitude. So the map from p to n of p is defined away from the bad points, and we want to understand its topological properties.
So you're thinking of b of p as an element in the tangent space at each of these points?
The Hamiltonian is b of p dot sigma. So
you're thinking of this vector as being a vector in the tangent bundle, right?
P is a function on a torus, the Brillouin zone. B of p is a 3-component function. It does not have the geometrical interpretation you're asking for. B of p is simply a 3-component function on the torus. So the sigma matrices act on a 2-dimensional space of quantum mechanical states that we haven't given any particular physical interpretation to. We're just studying a system of 2 bands about which I'm telling you nothing else. And the sigma matrices are the 3 traceless matrices that can act on these 2 bands. The most general form of the Hamiltonian, after subtracting from a multiple of the identity that doesn't affect band crossings, is some function b of p dot sigma, and I'm telling you nothing else about b of p. There are isolated points where b of p is 0, and away from the isolated points, we can define a unit vector n of p, which is b of p divided by its absolute value. And so this mapping from p to n of p is defined away from bad points. Now let's consider just one of the bad points, say at p equals p star, and let S be a small sphere around the bad point. This is really topology, so it doesn't have to be geometrically a sphere, just topologically. S is topologically, it's a little two-sphere that surrounds the bad point. So in particular, by definition, we have an isolated bad point. S is small enough it doesn't need any other bad points. So the map from p to n of p is defined everywhere on the sphere, little s. So this map is defined on a sphere, and n of p lives in a different sphere, because n of p is a unit vector. So the mapping from p to n of p is a mapping from one 2-sphere, which is S, to another 2-sphere that's parametrized by the unit vector n. Now, a continuous mapping from one sphere to another sphere of the same dimension always has a winding number or wrapping number, which is the net number of times the first sphere wraps around the second. P lives on the Brillouin zone, but we removed some bad points, and we voluntarily decided to restrict P to a little 2-sphere around the bad point and just discuss what happens there. Later on, we'll look at the rest of the Brillouin zone, but for now, we're only looking at P, which happens to lie in a little sphere S around one of the bad points. So on that little sphere S, the mapping from P to n of P is a mapping from a sphere, namely S, to another sphere, namely the sphere that is parameterized by the unit vector n.
But the surrounding of P is not a volume, it's just a part of the surface on that topology. Why would you...
I'm going to stick with what I've said, which is that I am voluntarily looking at the situation on the little sphere S. And P, just on the little sphere S, the mapping from P to n of P is a mapping from one sphere to another. And the mapping from a sphere to another sphere of the same dimension has an integer invariant, which is one of the most fundamental invariants in topology, really. It's the winding number of one sphere mapping around the second. So its existence reflects the fact that the homotopy group pi n of S n is Z, although actually, in a sense, it would be better for us to use homology and to write the same equation, same statement, with capital H for homology rather than pi for homotopy. But anyway, there's a fundamental integer valued invariant of a mapping from one sphere to another sphere of the same dimension. In this case, we take a sphere around the bad point, and the mapping from P to n of P is a mapping from one sphere to another, and then we have an integer invariant, which is the winding number of one sphere around the other.
So sorry, why would it be more convenient to think of homology?
Well, I'll use homology in a while. So before developing any general theory, let's see what the winding number is in the case of the relativistic Dirac Hamiltonian, where the sign is the fermion chirality. So let me proceed and then see if you have questions there. Let me finish with this derivation, and then we'll answer questions about it. For this Hamiltonian, what I call B of P is simply P itself. So n, which is a unit vector in the B direction, is just P divided by its absolute value. The bad point for this Hamiltonian, where the bands are degenerate, is the point where P is 0. And we can take the sphere that surrounds the bad point to be the unit sphere where P is 1. And if P is 1, then in absolute value, then n is simply plus or minus P. So the map from the sphere S around the bad point to the n sphere is just that n is plus or minus P. So this is the identity map of winding number 1 in the case of a plus sign, and it's minus the identity map, which winds around in reverse with winding number minus 1 in the case of a minus sign. So what we get from the Dirac Hamiltonian is actually the simplest example of maps of winding number 1 or minus 1. Now, the Nielsen-Ninomiya theorem is a statement that the sum of the winding numbers at bad points is always 0. Generically, in the absence of lattice symmetries that would lead to a more special behavior, a bad point of winding number bigger than 1 in absolute value is always unstable against splitting up into several bad points of winding number plus or minus 1. So there are situations in condensed matter physics where lattice symmetries make it natural to have bad points with a more special behavior. But in our derivation here, we're ignoring the possibility of symmetries. And in the absence of symmetries, the generic behavior is that every bad point has winding number plus or minus 1. So in that case, the statement that the sum of the winding numbers is 0 means that there are equally many Massless Weyl fermions of one chirality or the other. When there are bad points of higher winding number, the low energy physics is unfamiliar relativistically. It's essentially non-relativistic. So the Nielsen-Ninomiya theorem is a more general constraint that ensures that the low energy physics is always consistent, but it involves considerations that will be unfamiliar relativistically. But when the bad points have winding number plus or minus 1, the vanishing of the sum of the winding numbers means there are equally many gapless modes of positive or negative chirality, as the relativistic field theorist would expect for anomaly cancellation. So the Nielsen-Ninomiya theorem is completely general and allows any values for the line numbers at bad points. But the case that will be familiar to a relativistic physicist is also the case that's generic if there are no symmetries that make something else